Yoonseo, please review in about 2 minutes what you've drawn so far in an inverter design.
Okay, so basic concept of how signals are transformed in an inverter, how they're summed up, how they're compared, and then we'll go over it in the basic terms.
Mm-hmm.
So you first start off with the carrier wave. This is you first start off with a square wave that goes...
So DC input.
Yes, DC input, then through a regulator into a circuit that allows you to produce high-frequency carrier waves, maybe, say, 50 kilohertz, but it could also go into megahertz, but there's implications that we'll cover later on. We start off with a high-frequency square wave, and then through some other circuitry, we transform that into a high-frequency triangle wave.
Mm-hmm.
As long as it has some kind of diagonal element of change in the voltage, that's what we want. And then this triangle wave, high-frequency triangle wave, is going to become our carrier wave. Now there's also going to be the second aspect, which is the reference sine wave. Now this reference sine wave, familiar with sine, it goes like that, and then its frequency is the frequency we want for our output, so 50 to 60 hertz, and this reference sine wave needs to get amplified to amplified version where we have a higher peak and lows.
They're coming in a few minutes. That gets rectified to...
Amplified.
Amplified
yes.
to...
amplified to a higher peak and low.
Which the values don't matter at this point.
The values don't matter at this point. It's just higher and lower at the peaks and the bottoms.
Okay.
Yeah. And so we have the high frequency triangle wave, which is our carrier wave, and we have the amplified sine wave, which is our reference, right? And now what happens is, once you compare, the concept of a comparator is that it's a black box, you have two inputs and one output, right? And the two inputs are of different electric potential, so there's a different voltage assigned to each, and it changes, right? And the output is V3. Now V3 can be high or low depending on the inputs. Now if one of the inputs, if the first input is higher than the second input, then say it's a high. And then if the second input is higher than the first input, then the output is a low. You with me?
Yep.
Okay, so that's essentially how a comparator works, and the extent of the high and low is determined by the power to the comparator, V positive here and V negative here.
Nice.
Yes. So the comparator takes in two inputs, sees which of them is higher, and if the first one's higher, then it inputs a high voltage. If the second one's higher, then it's a low voltage output.
And for example,
Gotcha.
V plus and V minus might be 120 and 0 or no?
More like, say, 5 and 0.
Oh, really? At this point?
Yeah, at this point still. Yep, that's how it works. So now we have this understanding of the comparator, basically. It takes in two inputs and puts us an output based on which input is higher. Then we can refer back to our high-frequency triangle wave and our amplified sine wave and see that. I'll draw a graph of both of them at the same time. You have... Oh, yes, there's also actually... high frequency. There's another graph I'm missing. So we also have a low frequency square wave that we can't miss. And this low frequency square wave deals with at the same frequency of the sine wave, so 50 to 60 hertz, somewhere between there for normal AC output, and it looks like this, just like that. Right? And so we have three things actually. So we have the low frequency sine square wave, or actually it should better be called the output frequency sine square wave, and we have the triangle wave, high frequency triangle wave, and we have the amplified sine wave, which also is at our output frequency. Okay, so let's review that one more time. Output frequency square wave, high frequency triangle wave, and output frequency amplified sine wave.
Are these two in phase?
Yes. So this square wave is in phase with this sine wave. So we have these three waves down. I'll actually redraw them here. So what happens first is you sum the triangle wave, and the square wave. The square wave that's operating at output frequency. And what happens is, remember we had the triangle wave that is like that, and the square wave was going like this, right? Like this is not the scale, because this triangle would actually be something real much faster. But what happens is you get superposition. The concept of superposition is that when you have two signals that are close together, well, that are on top of each other, then you get the sum of the two signals. So what you actually get, if the square wave and the triangle wave are put together, is
a jittery square wave.
Exactly, a jittery square wave that works like like that. Okay, and now this is what happens when you sum the triangle wave and square wave together. And if we combine this into, if we take this output into a comparator, one input into a comparator, and then we take our sine wave, remember, our sine wave into the other input of the comparator, then you can see that the output of the comparator is going to be, let's first see the different waveforms in the superposition graph here, voltage and time. So it's going to be like that, and then that. And you're going to have a sine wave that's exactly like that, and like that. Right? Yeah. So whenever the sine wave is greater than the position of the triangle wave, then the comparator is going to be switching high, for instance. And then whenever the sine wave is lower than a certain position of the triangle wave, then the output of the comparator is going to be low. So what you get actually is that the higher the sine wave, well, the higher the voltage of the sine wave for the first half of the sine wave frequency, then you get a longer activation of the comparator. So it's more frequently higher the higher the sine wave gets. So, okay, this is the difficult part, because we're combining all the superpositions together. You get it?
Yeah, you're basically setting a velocity on another signal.
Yes. So let's take some examples here for clarification. So, for instance, from time, because this is a graph of voltage and time, from 0 to, say, to the peak here, from 0 to, say, 5 seconds, no, that's just an arbitrary value, you have the sine wave increasing in voltage, and the sine wave is above the triangle wave.
It's a different color.
Yes. The sine wave is above the triangle wave for this section of time, and then the triangle wave is higher than the sine wave, and then the sine wave is higher than the triangle wave for this section of time, and then this section of time. So as you can see, it's like that, and then once it goes down, you have the sine wave greater at this interval, but not there, and at this interval, and like that. And down here just a bit. So what happens is the comparator outputs a greater duration of a high value the closer you get to the peak of the sine wave, and outputs a lower duration of high value as you go off from the peak, as you can see by the activation here. So if these green sections represent the time duration of the high component of the comparator, of when you get a high output, you can see how it increases from, at the lowest point of the sine wave, it's very low, the duration is very low, and then as the sine wave increases, you get a higher and higher duration of high output, then a lower and lower. Now, how does this separate duration of high outputs relate to the inverter? Well, you put this signal, in the end, what kind of signal you get is like this. Let's actually start. This is now called the pulse width modulation graph, and because the comparator only has two outputs, only a high or low, what we get is